Namaste and welcome back to Avinashee Tech. In this video, we are going beyond just displaying text on an LCD. We are here to build understanding. Our goal isn't just to show you code that works, but to help you connect the dots, to read data sheets, understand how components talk to each other, and eventually make sense of the code, so you can even port it to other microcontrollers with confidence. We will start with the hardware in this part, that is the classic 16x2 LCD module and how it communicates over I2C using the PCF8574 GPIO expander. Then we will dive into the HD44780 controller's datasheet, the brain behind most character LCDs, and understand the commands it responds to and how characters are actually rendered. In the next part, we will bring it to life using ESP IDF. No Arduino IDE here. So you can see exactly what's going on under the hood and how I2C communications are implemented. By the end of this video series, you will be displaying both built-in and custom characters on the LCD, while understanding what the code is actually doing and why. So if you are tired of blindly copying code and want to actually grasp how things work, you are in the right place. At Avinashee Tech, we bring embedded systems to life, one wire, one byte, one project at a time. If you are into hands-on builds, deep dives, and code that actually makes sense, hit subscribe and join the tribe. Alright, it's hardware time. Let's first look at the pinout of our 16x2 LCD display. Starting from the left, we have power related pins VSS, VCC, and VEE for ground, supply, and contrast control. At the end, we also have LED plus and LED minus for the backlight. In between, we have got control pins RS, RW, and EN. And finally, data pins DB0 to DB7, which is used to send commands or the characters to the LCD. Now you don't always have to use all 8 data pins, that is D0 to D7. You can operate the LCD in 4-bit mode too, in which case you send each byte in 2 halves, therefore connecting D4 to D7 data pins only. Rest the power pins and the control signals are as it is connected. But even with 4-bit mode, the number of wires are pretty serious. Let's count it. 3 for power supply, 3 for control signals, that makes it 6, then 4 for 4-bit mode, let's make it 10, and then LED plus, LED minus, roughly 12. So still the number of pins are pretty much. Enter the PCF8574 I2C IO expander. This neat little module converts I2C into parallel I/O, and it's a great way to reduce pin usage using just 2 wires, SDA and SCL. Okay, 4 wires with power, but still that's less clumsy. So this module kind of sticks into the back of our LCD. Something like this. If we open up the data sheet of PCF8574 chip, well, there's a ton of information, but let's focus on the key parts. First, it expands I/O using just 2 lines of I2C. Great. Then we have the pin function. SDA and SCL are used for I2C communication, address lines A0, A1, A2 to set up device address, and I/O pins P0 to P7. The chip works within 2.5 volt to 6 volt and supports standard I2C clock frequency, that is 100 kHz. Scrolling down, we find the functional block diagram. The I2C lines and address inputs go to the bus controller, which eventually passes serial data to a shift register. The shift register then distributes the data to respective parallel I/O ports. There are internal D flip-flops used here. If the data bit is 1, the Q output is high. This Q output connects to an inverting buffer, which flips it, giving us logic 0 at the gate of PMOS and NMOS, turning PMOS on while keeping NMOS off. PMOS turns on when VGS is negative and below VGS threshold, which let's consider it is because gate is low and source is at VCC. So we get a weak pull-up at the I/O pin. If the data bit is 0, we get logic 1 at the gate of PMOS and NMOS. The PMOS turns off and the NMOS turns on. NMOS turns on when VGS is positive and above VGS threshold. So assuming it is above threshold, it pulls the pin low, giving us active drive. Down the data sheet, we find I2C address map. The address is 7 bits plus a read-write bit. That makes it 8 bit. If the last bit is 1, it's a read. If it's 0, it's a write. Now here's the schematic of the module that we are using. On this module, you can see A0, A1 and A2 are all pulled high. These are shoulder bridges on the module, and that gives us the last entry on this address table. So write address is 4E and read is 4F. Now if I shift the write address, that is 4E write by 1 bit, since the RW bit is not part of our 7-bit device address, I get hex of 27 as the device address. Now if you would have chosen some other pattern of A2, A1 and A0, let's say high, high, low, which gives a write address of 4C, that would have made the 7-bit address 26, hex of 26. So that is how you calculate address. Alright. Now the I2C lines in the schematic are connected through pull-up resistors, which is required for proper I2C operation. The I/O pins are wired like this: P0 to RS, P1 to RW, P2 to EN, P3 is responsible for LED backlight, LED plus, then P4 to P7 are connected to data pins D4 to D7. So D0 to D3 are left unconnected. Remember, we are using 4-bit mode, where each byte would be sent as 2 half bytes. Lastly, there's a jumper here for the LCD backlight. Keep it connected to enjoy a visible display. Alright, we have now understood the full setup of this LCD with our PCF8574 based IO expander. Let me now open up LCD controller chip HD44780 datasheet. So, HD44780 is a dot matrix LCD display controller from Hitachi. This chip includes everything you need in order to display your favorite characters, all in one package. If we scroll down the datasheet, we will find a block diagram. Now on the far left, we see the MPU interface with control pins RS, RW and E, along with data pins DV0 to DV7. These pins will be controlled by our PCF8574 I expander, which communicates with our controller via I2C. Moving to the right, we notice two registers: the instruction register, used to send commands like clear display, move cursor, etc., and the data register, which is used to send or receive display character data. Going one more step to the right, we see three important memory blocks: DDRAM, CGRAM, and CG-ROM. We will dive into these in just a bit. Finally, on the far right, we have common signals and segment signals, and these are used to finally illuminate character pixels, or in our case, dots. Now, if we scroll down to the pin function table, we can break down the roles of each of our pin. So RS determines whether the data coming in is a command or character data. RW selects whether we want to read or write. And E, or enable, starts the data read and write operation. The pins DV0 to DV7 are bidirectional, used to send or receive data between the microcontroller and the LCD controller. Now, let's talk about DDRAM, or Display Data RAM. This section stores characters as 8-bit character code, and it has a total capacity of 80 characters. Depending on your display type, each visible character on screen will have a corresponding DDRAM address. For our 16x2 display, the address layout looks like this. So line 1 ranges from 0x00 to 0x0f. Line 2 starts from 0x40 to 0x4f. So in short, DDRAM address tells you where the character appears on the screen of our LCD display. The DDRAM data, which is 8 bits, tells you what character will appear, obviously as a 5x8 dot pattern. Not all DDRAM addresses are used, and that is why Hitachi even suggests that the unused locations can be treated as general purpose RAM. Cool. Next up, we have CG-ROM, or Character Generator ROM. This part generates predefined characters based on their 8-bit character codes, the same ones which are stored in the DDRAM data. Now, this is the table of ROM code A00, and below it we have a table of ROM code A02. So different ROM code provides us with a different list of characters. Let's see ROM code A00. So this includes ASCII characters. Let's open up ASCII table and look up for the capital A letter. So this is hex of 41. Now we head to ROM code table. Upper 4 bits 0, 1, 0, 0, lower 4 bits 0001. Boom. That's your A character. Alongside ASCII, the ROM also includes Japanese Kana characters. Before we dive into that, let me just say, my Japanese is about as good as America's diplomacy. Anyway, if you look for the character Kui, I don't know if I'm pronouncing it correct, but let's say it's Kui, then this character, it's at 0 hex B7, and just above this character we have Ka, so that's 0 hex B6. Cool. Kui Ka. Below the Kana table there's ROM code A02, which adds European characters as well and is great for multilingual support. So in summary, CG-ROM contains the actual dot patterns that will be shown based on the 8-bit character codes. Now let's talk about CG-RAM or character generator RAM. So this is where you can create your own custom characters. The HD44780 supports either 5x8 or 5x10 dot characters. But that's a limit. CG-RAM only has 64 bytes of space. In 5x8 mode, each character takes 8 bytes, so you can define up to 8 custom characters. But in case of 5x10 mode, each takes along 11 bytes including the cursor, so you are limited to 4 characters. I suppose it's due to memory alignment of 16 bytes. So this is 5x8 dot character patterns and this is 5x10 dot character patterns. You can see that 11 byte is used for this character pattern while 5 is left. And they have even stated here, since lines 12 to 16 are not used for display, they can be used for general data RAM. Alright. Now let's look at how these dot patterns are formed. So each row is represented by a byte and the bits determine which dots are lit up. A 1 lights up a dot. A 0 leaves it off. So a full character pattern is just a group of bytes defining a pixel matrix. CG-RAM addresses are 6 bits wide and each address points to a byte of that particular pattern. Now here's the interesting part. To actually display a custom character pattern from CG-RAM, you must send a character code between 0 to 7 to DD-RAM. Those codes are reserved to map directly to CG-RAM entries. We will see this in action in the code section later. If you scroll down further in the datasheet, you will find a list of instructions like clear display, return home, entry mode set, and all that. Finally, once the character code is loaded and the pattern is known, the chip uses a combination of common and segment signals to illuminate the dots and draw the character. Something like this. You can even spot the cursor in this diagram in a 5x8 layout. It's shown as the last byte in the pattern just below the letter I. So, in summary, DD-RAM is what to show, a character code. CG-ROM or CG-RAM are how it appears or the pixel pattern for that particular character code. LCD is where it shows, which is mapped via segment plus common lines. Alright, enough with the datasheet. So that wraps up part 1, where we explored how the HD44780 LCD controller works under the hood and how the PCF8574 I/O expander helps us interface it efficiently with the ESP32 using I2C. In the next part, we will dive into actual coding and hardware setup using ESP-IDF to drive this LCD display. Make sure to like, share, and subscribe to Avinashee Tech so you don't miss the hands-on implementation. Hit the bell icon and drop a comment if you have questions or want to see other display modules in future videos.